Well, my title is somewhat mysterious, Springs in Honey, but it's really about perspective of a physicist, maybe a bit of a mathematician, on something that's living and moving. And so the question we ask ourselves is, how do microorganisms move? And so as you see, these guys come in a variety of shapes and forms. And so these are bacteria that tend to have these long appendages called flagella, whereas these guys, ciliates, they have somewhat shorter hairs, and they move these hairs in order to propel. And so there is a huge variation in the modes of their swimming. But the common denominator is that they all have these filamentous appendages with the cilia or flagella, and they move them in a fluid. And we want to explore that in more depth. So to give you a flavor on how these guys move, so these are moving E. coli. So what they do, they have a bunch of these flagella, they bundle them together, and they rotate them counterclockwise, and by that they propel forward. But then sometimes they start moving them clockwise, and this bundle spreads out, and by that they turn, which is called the tumble, and then they bundle it together again, moving them counterclockwise. And so this is a so-called run and tumble motion of bacteria. Now, ciliates, these guys are slightly different, so they move these little hairs in a concerted manner, which is called a metachronal wave, which is very akin to a Mexican wave in a stadium. And by that, they push the fluid to the side, and this colony of algae is able to rotate by stirring the fluid around it. Now, we want to look at the motion of this fluid that is driven by the motion of these hairs. And so here's where the honey comes in. Because if you want to look at a certain flow, one question you can ask is, well, given the length and velocity in my problem and the properties of the fluid, how does this flow look like? Is there any general feature of it? There is a difference when you're stirring a jar of honey and when you're stirring water in a swimming pool. And this difference is quantified by the Reynolds number, which is a dimensionless number that measures the relative importance of inertial effects to viscous effects in a fluid. And so it's just the density of the fluid times the velocity times the length over viscosity. And the mathematical fact is that the equations of motion of these fluids look similar when these flows have similar Reynolds numbers. And I'll explain in a moment what that means. And for swimming microorganisms, I'll just tell you that this Reynolds number is very small. It's very close to zero, and therefore inertial effects don't really matter as compared to viscous effects. So it's a so-called low Reynolds number flow, or a slow viscous flow. And you can achieve low Reynolds numbers in a variety of ways. So either you can have relatively large lengths of your flow and small velocities and very large viscosities, which happens when you look at a flow of glaciers, which are large but super viscous, the flow of lava, and also honey on a spoon. So these flows have a very low Reynolds number. On the contrary, you can have very small length scales of order of micrometers and very small speeds at moderate viscosities, which happens in the case of bacteria in water. And these flows are mathematically similar. So they look similar. They have a similar character. And the conclusion for us is that the same underlying physics means that microorganisms, they feel like if they were swimming in honey. So if we were swimming in honey, we would feel roughly the same way as they do. And that imposes very serious limitations on their motion. And that's why they look different from, let's say, swimming fish. And they use different strategies to propel. So one fundamental thing about these flows is that the drag force that they feel moving through the fluid is proportional to the velocity. And, well, somewhat mysteriously, if there is no force, there is no speed. So if I stop pulling something through the fluid, it would come to an immediate stop, which is not the case in a swimming pool. If you stop stirring the fluid, you still move forward because of inertia. But there is no inertia in this world. And also, these drag forces are directional. So in this movie, you see a sedimenting rod in a bathtub full of glycerin or honey. And so you can see that it moves slightly sideways. That means that there's a different drag force in the direction along the motion and perpendicular to the motion. Now, if you imagine your filament, a bacterial flagellum, as a filament, which bits of it are moving against the fluid around it, they feel various drag forces at various points. But if you sum all these forces, you get a thrust force that is balanced by a drag force on the body, and that means the bacterium is swimming. And swimming is about balancing propulsive forces and drag forces. However, these appendages are not stiff, so the flow has some coupling to the structure. And so I'll give you a quick tour of elastic filaments. And if you include elasticity, you can have a variety of phenomena related to elastic deformations induced by compression, like buckling of railroad tracks, or formation of structures just by exerting forces on elastic filaments. And so the main message is that deformations cost energy. If you want to deform an elastic filament, it wants to be straight again. And there are various ways in which you can compress a filament. You can twist it and you can bend it in different directions, and that all costs energy. And so if we want to quantify that, I'll just explain very briefly that energy of a compressed or a bent object depends on the shape of it by the fact that imposing a curvature costs energy, and also compressing it costs energy. And this expression just says that if I want to know the energy of a compressed or of a bent object, I need to sum up all these modes of deformation. So the more I deform it, the more energy it has stored. And it's fully analogous to a motion of a spring, which you stretch, and then you increase its elastic energy. And so the interplay of these two effects is something that is responsible for creation of shapes. In this very simple experiment, what we do is we push a piano string in a bathtub full of honey. So in the beginning, it is straight, and as I start pushing it, it starts deforming. And this is a simulation that shows basically how this happens. And if you look at the energy of this filament, you see that the total energy is basically, first, when it stretches out, it's stretching out against the fluid, so there is a drag force acting on it. And then, at some point, it's too compressed, so it has to release energy by buckling, by deforming, and then you decrease the total energy. The energy stored as compression is lower, but then more energy is stored in curvature. And so, to give you a more biological example, now that was a toy problem. The real problem we want to address is, for instance, a bacterial cilium we want to model. And if we look at this bacterial cilium, there's an interplay of more subtle effects, because that is an object that is driven by its internal active motors. So you have to think about these active driving forces that are distributed along the filament, that create internal tension and internal force moments, because it intrinsically wants to also stretch out. But moving in a fluid creates a hydrodynamic drag force, and balancing all these forces leads to a very complex kinematics. Now, it turns out that for a given filament length and thickness in this somewhat simplistic model, there is just one parameter that determines the motion that depends on the kinematics, on the rotation rate of the cilium, on its stiffness, that is this coefficient B, and on the drag coefficient of the cilium when it moves through the fluid. Now, putting all these ingredients inside, you get a beating pattern that is very similar to what we see in experiments, in which they do something called a power stroke, which they do like that, and then a recovery stroke, in which they go back to the original position. And so this is what comes out of computer simulations, and this is very similar to what we see in real-life experiments. And so to conclude, I wanted to convey a message that flows in microscopic systems are dominated by viscosity. And flexible filaments in flow are governed by a subtle interplay between elasticity and viscous drag. And well, you can complicate it sufficiently enough to come up with a model that is capable of grasping the resulting motion and flow that might be relevant to the understanding of very basic underlying biological processes. And with that, I would like to thank the group of Eric Lauga in Cambridge, in which some of these works have been done, and thank you for your attention.